All right, in this video, we will be going over section 1.6. This section is about infinite limits and indeterminate forms. All right, first, I want to give a motivation to what we mean by infinite limits. First, let's look at this particular example. Suppose you are asked to find the limit as x approaches to 1 from the right-hand side. You see this small plus sign. So as limit as x approaches to 1 from the right-hand side, 1 over x minus 1. What happens to this function as x approaches to 1 from the right-hand side? Let's see where it approaches, okay? For that, what I'm going to do is I'm going to take a bunch of x values which are approaching to 1 from the right-hand side. As you can see, this is 1.1, 1.0001, 1.001, 1.0001, 1.00001. Okay, as you can see, these values are approaching to 1 from the right-hand side. Then I can calculate my x minus 1, which is the denominator here. Okay, so here are the values of x minus 1. As you can see, as x approaches to 1 from the right-hand side, your x minus 1 approaches to 0, right? These values are getting smaller and smaller, but these values are approaching to 0 from the right-hand side because all these values are positive, right? But approaching to 0. So that means this x minus value, the value of x minus 1 approaches to 0 from the right-hand side. That means as x approaches to 0 from the positive side, the limit of this expression takes the form 1 over 0 plus. 0 plus means this quantity approaches to 0 from the right-hand side, okay, as x approaches to 1 from the right-hand side. So the form of the limit of this expression is 1 over 0 plus. What is 1 over 0 plus? Well, to get an idea, again, we can compute our function value at each of these x values chosen, okay? As you can see, as x approaches to 1 from the right-hand side, your function values are growing, right? They are growing without bound. So that means, looks like from this table, it looks like as x approaches to 1 from the positive side or from the right-hand side, your function value is approaching to infinity, okay? In fact, the limit of this one is infinity. If you take a limit of this form 1 over 0 plus, the limit value, we say that the limit value is infinity, or in other words, as x approaches to 1 from the right-hand side, the function value approaches infinity. All right, then we have this theorem 1.29, limits whose denominators approach 0 from the right or the left. Okay, so here is the first part. Here is what the first part tells you. Limit as x approaches to, if limit as x approaches to c, f of x over g of x is of the form 1 over 0 plus, then limit as x approaches to c, f of x over g of x is infinity. Okay, when you try to calculate this limit as x approaches to c, if you get this form, that means the limit is infinity. That's what it tells you. Here is an example. Let's try to calculate the limit as x approaches to 1, this expression. As you can see, as x approaches to 1, what form are you going to get for this expression? You are going to get 1 over 0 plus, right? Why 1 over 0 plus? Why does it approach to 0 from the right-hand side as x approaches to 1? Notice that as x approaches to 1, this quantity is approaching to 0, but you are taking the square here, right? That will make this whole thing positive. Okay, still, this positive quantity is approaching to 0 as x approaches to 1. Okay, that's why I'm saying 1 over 0 plus. Okay, so this expression approaches to 0 from the right-hand side. So the limit should be positive infinity in this case. Okay, so you can experiment these things actually. What do you mean by 1 over 0 plus? That means try to put some small and small number, very small number here. You will see that this whole number is going to be a very big number when you put very small number in the bottom. Okay, that's the idea. when the bottom approaches to 0 from the positive side, this whole thing will approach infinity. All right, next part is, if limit as x approaches to c, f of x over g of x is of the form 1 over 0 minus, then limit x approaches to c, f of x over g of x is equal to minus infinity. Okay, so if when you try to calculate this limit, if you get this form 1 over 0 minus, the limit would be minus infinity. That's what it tells you. Here is an example. Limit as x approaches to 1, this expression. What happens to this expression? Limit as x approaches to 1. You get 1 over 0 minus, right? This time, as x approaches to 1, notice that this quantity is a positive quantity which approaches to 0, but this negative sign will make that quantity negative. Okay, so this whole, as x approaches to 1, this whole thing approaches to 0 from the left hand side because of this negative sign. Okay, so we get the form 1 over 0 minus. Okay, if you get the form 1 over 0 minus, your limit is minus infinity. Okay, you have to have minus sign. All right, of course, these statements are valid even for one-sided limits. Okay, even for right and left limits, they are valid. If a limit as x approaches to c from the positive side, f of x over g of x is of the form 1 over 0 plus, then limit as x approaches to c from the positive side, f of x over g of x is infinity. Okay, here is an example. As you can see here, limit as x approaches to 3 from the positive side, this expression takes the form 1 over 0 plus, right? Why plus? Because x is approaching to 3 from the positive side. Positive side means the numbers bigger than 3. Positive side means the right hand side. Okay, as x approaches to 3 from the right hand side, when x approaches to 3 from the right hand side, this x is a number bigger than 3. So that means this quantity is a positive quantity, but it approaches to 0 as x approaches to 3 from the right hand side. So it takes the form 1 over 0 plus, which is infinity. That's what it tells you. Okay, and then the last part, if limit as x approaches to c from the right hand side, when I say right hand side, an equivalent way of saying that is the positive side. Okay, positive side and the right hand side, they are equivalent. If limit x approaches to c plus f of x over g of x is of the form 1 over 0 minus, then limit x approaches to c plus f of x over g of x is infinity. Okay, minus infinity, pardon me. This should be minus infinity. Minus sign is missing here. Make sure that you put a minus sign. Right, here is an example. Look at this example. Limit x approaches to 4 from the right hand side. Plus means right from the right hand side. What happens to this expression? As you can see, as limit x approaches to 4 from the right hand side, this quantity is a negative quantity, but it approaches to 0, right? So we get the form 1 over 0 minus. So the limit is minus infinity according to this theorem. Okay, this is minus infinity. Okay, all right. Let's move on. And next, we have this theorem 1.30, limits whose denominators become infinite. Limits whose denominators become infinite approach 0. Okay, what does this mean? Here is the first part of the theorem. If limit as x approaches to infinity, f of x over g of x is of the form 1 over infinity, then limit as x approaches to infinity, f of x over g of x is equal to 0. That means when you calculate this limit as x approaches to infinity, if you get this form, then the answer is 0. The limit value is 0. Okay, here is an example. Look at this example. As x approaches to infinity, 1 over x plus 1. What happens to this function as x approaches to infinity? You get 1 over, of course, here as x approaches to infinity, this part goes to infinity. This looks like infinity plus 1, which is again infinity, right? 1 cannot make any effect to infinity. So infinity plus 1, it also takes the form infinity. So you have the form 1 over infinity. That means your answer is 0. Okay. All right. Next, if limit as x approaches to infinity, f of x over g of x is of the form 1 over minus infinity, again, the limit as x approaches to infinity, f of x over g of x is equal to 0. Or in other words, when you try to calculate this limit, if you get this form, your answer is 0. Okay, the limit value is 0. Here is an example. Limit as x approaches to infinity, 1 over 1 minus x. As you can see, as x approaches to infinity, this becomes infinity, but you have a negative sign in front. You have a negative infinity there. Okay, you have a negative infinity there, but this is a finite number. It cannot make any effect to the negative infinity. So your form would be 1 over minus infinity. Okay, so the answer is 0 by this theorem. If you take this form, the limit value should be 0. All right, let's move on. Here is another very useful theorem that we will be using frequently. This is theorem 1.31, limits of some basic functions at infinity. Okay, if k is a positive number, then limit as x approaches to infinity, x to the power k is always infinity. Okay, and limit as x approaches to infinity, x to the power minus k is equal to 0. Here are some examples. Okay, look at this example. As you can see here, this looks like this, right? With k is positive, x to the power k is positive. In this case, your k value is 2, which is a positive number. In that case, your limit should be infinity. Actually, it is clear. If you look at the graph of this function, what is the graph of x squared? Y is equal to x squared. It looks like this, right? It looks like this. What happens to this function value, x squared, as x approaches to infinity? Your y values are also growing, right? When your x is getting bigger and bigger, your y values are also getting bigger and bigger. They are growing without bound. So that means the y value approaches to 0. Okay. So this theorem can be used here onwards. And then limit as x approaches to infinity, x to the power minus k is equal to 0. Here is an example. Limit as x approaches to infinity, x to the power minus 3. As you can see here, you have a negative number as a power. What happens is that if you view this as limit as x approaches to infinity, instead of x to the power minus 3, I'll write 1 over x to the power 3. My power doesn't look good. Okay, 1 over x to the power 3. Now, as you can see, as x goes to infinity, this takes the form 1 over infinity, right? So what is the answer? If that takes the form 1 over infinity, the answer would be 0. Okay. So if something takes the form 1 over infinity, the limit value is 0 from the previous theorem. Okay. All right. And the next part is, again, if k is bigger than 0, then limit as x approaches to infinity, x e to the power k times x is infinity, and limit as x approaches to infinity, e to the power minus kx is equal to 0. Okay. Here are some quick examples. As x approaches to infinity, e to the power 2x is equal to infinity by this theorem. If you have a positive number here, but if you have a negative number there, limit as x approaches to infinity, say e to the power minus 2x this time, that is equal to 0. Okay. And here is the third part. Limit as x approaches to infinity, ln of x is equal to infinity. This is also clear from the graph of ln x. You all know that the graph of ln x looks like this, right? So what happens to ln x as x goes to infinity? As x goes to infinity, your y value is growing without bound. Your function value is growing without bound. So that means your function value also should go to infinity. So your answer is infinity. And then the fourth part, the function sin x, cosine x, tan x, secant x, cosecant x, and cotangent x all have periodic behavior as x goes to infinity, and thus their limits as x approaches to infinity do not exist. Okay, this is clear. For example, take sin x. The graph of sin x looks like this, right? It will continue forever. The left-hand side as well. As you can see, we cannot determine what happens to the function value as x goes to infinity because it keeps bouncing, it keeps oscillating. Okay, so the limits of the trigonometric functions as x approaches to infinity do not exist. Okay, and here are some other useful result. Limit as x approaches to infinity, tan inverse x is equal to pi over 2, and limit x approaches to minus infinity, tan inverse x is equal to minus pi over 2. Again, this is also clear when you look at the graph of tan inverse. Tan inverse x, okay? Let's say y is equal to tan inverse x. As you can see, the graph of y is equal to tan inverse x looks like this, with this being pi over 2, and this is minus pi over 2. So these two limit statements are clear from the graph of tan inverse x. Okay? As x approaches to infinity, your y value, your function value is approaching to pi over 2. That's how you get this pi over 2 here. Similarly, you get minus pi over 2 as x approaches to minus infinity. Okay. All right, let's move on. Next, we have this very interesting theorem. This theorem is called the horizontal asymptote theorem for rational functions. Let's see what this theorem tells. Okay. If f of x is equal to p of x divided by q of x is a rational function in which the polynomials px and qx have leading terms an times x to the power n and bm times x to the power m respectively, then if n less than m, if n less than m, then the graph of y is equal to f of x has a horizontal asymptote at y is equal to 0. Okay. First of all, let's recall a few things from your pre-calculus class. Suppose your polynomial is this one. F of x is equal to 2x cubed plus 4x squared plus 7x plus 1. Okay. So what is the leading term of this polynomial? Okay. Leading term is the term with the highest degree term. Take this first term here. Of course, this is the highest degree term. This is what we mean by the leading term of this polynomial. Okay. All right. Let's go back to the theorem. What this theorem tells you is that if you have a rational function of the form p of x over q of x, and the leading term of the numerator is of this form n times x to the power n, and the leading term of the denominator is of the form bm times x to the power n. Then if the degree of the numerator is smaller than the degree of the denominator, then your horizontal asymptote is y is equal to 0. Let's look at an example to understand this. Okay. Let's say f of x is equal to x plus 1 divided by x cubed plus 2. As you can see here, what is the degree of the top? N is the degree of the top. Okay, remember this n given here is the degree of the top polynomial p of x. In this case, my p of x is this one, which is in the top. Okay, so what is the degree of that polynomial? It is 1, right? Clearly it is 1. And what is the degree of the bottom polynomial? Degree of the bottom polynomial means degree of this polynomial, which is m. Okay, so what is the degree of my bottom polynomial? Which is 3. M is equal to 3. Notice that my n is less than m in this case. See, 1 is smaller than 3. N is smaller than m. If that is the case, my horizontal asymptote is y is equal to 0. This theorem immediately gives you a way to find the horizontal asymptote using this criteria. Okay, horizontal asymptote is y is equal to 0, because the degree, because your degree of the top is smaller than the degree of the denominator or degree of the bottom. Okay. All right. Here is the second part. If the degree of the top and the degree of the bottom are equal, then the graph of y is equal to f of x has a horizontal asymptote at y is equal to a to the power n divided by b to the power n. If the degrees are equal, to get the horizontal asymptote, what you do is you divide these two coefficients. You divide the coefficient of the leading term. This is called the leading coefficient of the top. Notice that this is the leading term of the numerator and this is the leading term of the denominator. What you do is, in this case, when your degree of the denominator and the degree of the numerator are equal, you divide the leading coefficient of the top polynomial by the leading coefficient of the bottom polynomial to get the horizontal asymptote. It is as simple as that. Okay. Again, let's take an example. Let's say 2 times x cubed plus 5. In the bottom, you have 7x cubed plus 2x plus 1. As you can see, this time the degree of the top polynomial and the degree of the bottom polynomial are equal. Both n and m are 3. In that case, to find the horizontal asymptote, what you do is you divide the leading term of the top polynomial by the leading term of the bottom polynomial. So the horizontal asymptote would be, I'll write HA for the horizontal asymptote is y is equal to 2 over 7. That's what it tells you. Okay. All right. And the last part, if the degree of the top polynomial is bigger than the degree of the bottom polynomial, then my function f of x does not have a horizontal asymptote. Here is an example. Let's say your f of x is x to the power 4 plus 1 divided by x squared plus 2. Now, as you can see clearly, the degree of the top polynomial is bigger than the degree of the bottom polynomial. Okay, where n is 4, m is 2. Okay, notice that the degree of the top polynomial is bigger than the degree of the bottom polynomial. So, no horizontal asymptote. No horizontal asymptotes. Let me write it. No horizontal asymptote. All right, that is a very powerful theorem. This allows you to calculate, find the horizontal asymptotes of rational functions within seconds. All right, let's move on. Then we have this theorem 1.33, indeterminate forms for limits. Okay, for each of the following is an indeterminate form, meaning that a limit in one of these forms may or may not exist depending on the situation. Okay, these are the indeterminate forms. 0 over 0 is an indeterminate form. Okay, what that means is that when you try to calculate a limit, if you get this form, okay, you cannot say anything about the existence of the limit. Okay, limit may or may not exist if you get this form. That's why we say that this is an indeterminate form. Likewise, we have these 7 indeterminate forms: 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the power 0, 1 to the power infinity, and infinity to the power 0. All these forms are indeterminate form. Okay, I'll take an example only for this case. Think about this. Suppose you want to calculate limit as x approaches to 1, x squared minus 1 divided by x minus 1. Okay, so what is this limit? If you try to calculate this straight away by plugging this 1 in your function, if you plug in 1 here in the top, you get 0, right? In the bottom also you get 0. That means you get this form, 0 over 0 form. It is an indeterminate form, okay? But the limit of this function exists. The limit as x approaches to 1, x squared minus 1 divided by x minus 1 exists by cancellation law, okay? So the limit, if you calculate the limit, you will get limit as x approaches to 1, x squared minus 1 is x minus 1, x plus 1. In the bottom, you have x minus 1. Now, of course, you can cancel these two common factors and plug in x is equal to 1 in the remaining function. You get answer t, 2. Okay. As you can see, of course, this limit exists. Okay. But if you try to compute this limit, you get this indeterminate form. If you get this indeterminate form, limit may or may not exist. This is an example where actually the limit exists. Can you give me an example where you get this indeterminate form, but the limit does not exist? Can you provide me an example where you get this indeterminate form, but the limit actually does not exist? Well, try this one. Limit as x approaches to 1, I switch the top and bottom. At minus 1. Again, if you straight away try to apply the limit, if you straight away try to plug in this number, you will get 0 over 0, that is indeterminate form. Actually, in this case, the limit does not exist. Okay. So by cancellation law, you get x goes to 1 over x plus 1, right? Pardon me, I have a small typo here. This square should be actually outside, okay? This should be x minus 1 whole thing squared. All right, now by cancellation theorem, we get 1 over x minus 1, right? You cancel one of the factors, then you get this limit. Then, does this limit exist? No, this limit does not exist. Calculate the left limit and the right limit. You will see that you get plus infinity for the right limit and minus infinity for the left limit. In other words, get limit as x approaches to 1 from the positive side, 1 over x minus 1 is, it takes the form 1 over 0 plus. That means the answer is infinity. But if you calculate the left limit as x approaches to 1 from the negative side or the left-hand side, 1 over x minus 1 takes the form 1 over 0 minus. So that means the answer is minus infinity. As you can see, limits are different and limit does not exist because it's infinite anyway. Okay. So here is an example where you have the indeterminate form initially, but the limit actually exists. Here is an example where you have the same indeterminate form 0 over 0 if you try to plug in the number straight away, but this limit does not exist. Okay. All right. So these are the indeterminate forms that you need to remember. Okay. All these forms are indeterminate forms. Next, non-indeterminate forms for limits. Okay. Part 1, a limit in any of the forms must be equal to 0. Okay. When you try to calculate your limit, if you get this form 1 over infinity, then the limit has to be 0. If you get this form, then also the limit has to be 0. And for all these, the limit has to be 0. Let's do an example for one of these. For example, limit as x approaches to infinity 1 over x plus 1. What happens to this? This takes the form 1 over infinity, right? As x approaches to infinity, this becomes infinity. but this 1 cannot make any effect to infinity, so it takes the form 1 over infinity. So the answer is 0 by this theorem. Okay. Likewise, we can our limit will be 0 if we have any of these forms as well. Okay. All right. The next part, limit in any of these forms must be infinity. Okay. If you take this form 1 over 0 plus, the limit is infinity. And if you take the forms infinity over 0 plus, again, the answer is infinity. And here are the limits of this form. All are, the answer is infinity. Okay, the limit would be infinity if you take any of these forms when you try to calculate the limit. All right, let's move on. Then we have this very useful trigonometric limits. Two trigonometric limit formulas. Limit as theta approaches to 0, sine theta over theta is equal to 1. The other part is limit theta approaches to 0, 1 minus cosine theta over theta is equal to 0. Okay, so in this theorem, I want to prove the first part, and I'll leave the second part as an exercise. Okay, to prove the first part, I'm going to show the right limit case only. Okay, as theta approaches to 0 from the positive side, I'm going to show you that sine theta over theta is equal to 1. Okay, similarly, we can show that the left limit is also 1. Similar argument will show that theta goes to 0 from the left hand side, sine theta over theta is equal to 1, and hence this limit is 1, because your right limit exists and it is equal to 1, and the left limit exists, that is equal to 1. That means the two-sided limit exists, that is equal to 1. Okay, so I will only show this part, and this is very much similar to the first part. I'll show you. I will briefly explain how to show this one once you have proven this part. Okay, let's try to focus on this one. For that, I'm going to draw a picture. All right, here is my picture. I'm going to consider a segment of a circle of radius 1. The radius of my circle is 1. This is a segment. Okay, this is the arc, and this central angle is theta. We assume that theta is a very small positive value because we want to see what happens as theta, what happens to this function as theta approaches to 0. So we may assume that this theta is a very small positive number. Okay, so we have a segment, this angle is theta. And notice that from the basic trigonometry, I can find this height. What is that height? If I take this to be h divided by 1 is sine theta, right? That means h is equal to sine theta. So this is nothing but sine theta. Similarly, using simple trigonometry, we can see that this height would be tan theta. Okay. Now notice that I have this inequality. Tell me whether you agree with me or not. This sine theta is less than or equal to theta less than or equal to tan theta. Notice that if this is 1, if the radius is 1, what is this arc length? Remember, the arc length formula is SC is equal to r theta, right? The radius times the central angle. But in this case, my radius is 1. So my SC is just theta, right? Because radius is 1. So that means this length is just theta. But notice that clearly this arc length is bigger than this height, which is sine theta. So I have theta is bigger than sine theta, and clearly this arc length is less than this height. tan theta by the geometry of this picture. So my theta, the arc length, should be less than or equal to tan theta. Okay, that's how I get this inequality. Now, notice that I'm assuming that my theta is a very small positive number, right? Since I'm considering theta approaches to 0 from the positive side, I can divide this entire inequality by sine theta. Okay, I can divide the entire inequality by sine theta. Then you get okay, if you divide this entire inequality by sine theta, here is what you get. Of course, if you divide this by sine theta, you get 1. Here you get theta over sine theta. And if you divide this by sine theta, you get 1 over cosine theta. Now, I flip the top and bottom of every expression involved in this inequality. If you flip the top and bottom of the first quantity, first number 1, it is 1 itself, right? 1 means 1 over 1. If you flip the top and bottom, you get 1. But when you flip, you have to switch the inequality sign, right? So you get sine theta over theta greater than or equal to cosine theta over 1. I switch the top and bottom here, I get 1. I switch the top and bottom here, I get sine theta over theta. I switch the top and bottom here, you get cosine. Okay. When you switch the top and bottom, you have to change the inequality. Okay. I can do this because I know that all these quantities are positive because my angle theta is a very small positive angle. All right. Now what I'm going to do is I'm going to take the limit. Limit as theta approaches to 0 from the positive side, 1 greater than or equal to limit as theta approaches to 0 from the positive side, sine theta over theta greater than or equal to limit theta approaches to 0 from the right hand side, cosine theta. Okay. Notice that this limit is equal to 1, right? Because it's a constant. The limit of a constant is that constant itself, which is 1. What happens to this one? As theta approaches to 0 from the positive side, cosine theta. That also approaches 1, right? Because cosine 0 is 1. This is equal to 1. As theta approaches to 0 from the positive side, cosine theta is approaching to 1. So that is 1. As you can see, now we can apply the squeeze theorem. See, if you look at this function, as you can see, this function is stuck between these two functions, and the limit of this function as theta approaches to 0 is 1. Limit of this function is also 1. So the limit of this middle function should be 1 as well by squeeze theorem. By squeeze theorem, limit as x approaches to 0 from the positive side, sine theta over theta also has to be 1. Okay. Right. So we have this right limit. Here is how we can prove the left limit. Okay. We need to show that limit as x approaches to 0 from the left hand side, sine theta over theta is equal to 1. What you can do is you can do a change of variable. You can take theta is equal to minus k with k greater than 0. If k is greater than 0, automatically this theta is a negative number, right? But it is approaching to 0. That means theta approaches to 0 from the left hand side. Okay. And in that case, if you multiply both sides by minus, you get minus theta is equal to k. That means as theta approaches to 0 from the left hand side, k approaches to 0 from the right hand side because of this minus sign. So I can write this limit this way. Limit the k approaches to 0 from the right hand side, because I know that as theta approaches to 0 from the left hand side, my k approaches to 0 from the right hand side. Okay. Pardon me, as theta approaches to 0 from the left hand side, my k approaches to 0 from the right hand side. So I can replace this by k approaches to 0 plus. Now I have sine theta. Instead of theta, I'm going to plug in minus k. Sine minus k divided by, again, for the theta, I put minus k. But what is this? I can pull this minus sign out, right? Because it's sign. And then I can cancel that minus sign with this minus sign. Then you get sine k over k. Limit as k approaches to 0 from the positive side, sine k over k, which is 1. We proved that. As theta approaches to 0, this should be theta, by the way. As theta approaches to 0, plus 0 from the right-hand side, sine theta over theta is equal to 1. So this has to be 1. Okay, so we proved the left limit is also 1. That means the two-sided limit exists. Limit as theta approaches to 0, sine theta over theta is also 1. So we have established the result. Okay. Right, now let's look at some examples. Here is the example that I want to look at. Use limits to find any horizontal asymptotes of the following functions. Okay. How do you find the horizontal asymptotes? Basically, we want to find what happens to my function as x approaches to infinity, right? Would that be, would your y value be approaching to some nice number, L? In that case, we say that this y is equal to L. This horizontal line is a horizontal asymptote, right? So we want to check that. So how do we find horizontal asymptotes? Well, I have to find the limit of this. Let's work on the first part. To find the horizontal asymptote, I need to find the limit as x approaches to infinity, x over x minus 1. Okay. Now, if you straight away plug in the infinity to this function, you get infinity over infinity form. Remember, that's an indeterminate form. So we need to figure out a way to find this limit. Okay. So we use a small trick. The trick is that we multiply both top and bottom by 1 over x. Or you divide both top and bottom by x. You divide this expression by x. You divide the bottom expression also by x. Okay, let's do it and see what happens. Limit as x approaches to infinity. I'm going to multiply my top by 1 over x. And I'm going to multiply my bottom also by 1 over x. And see what's going on there. Okay, if I multiply my top by 1 over x, you get limit as x approaches to infinity, just 1 in the top, right? These two will be cancelled. Divided by, in the bottom, you get 1 minus 1 over x, right? If you multiply these two together, x times 1 over x, which is 1, and then 1 over x times 1, that would be 1 over x. Okay. Now you can take the limit. Why am I saying that? Now plug in infinity and see what happens. 1 over 1 minus, you have 1 over infinity form here, right? You just plug in infinity for your x. Then you have 1 over infinity form there. But what is the value of this form? If you have 1 over infinity form, what is the value? 0, right? So you get 1 over 1 minus 0, which is 1, of course. So we have the limit, okay? All right, let's look at the next example. We use a, oh, by the way, we're not done with that. We didn't write the horizontal asymptote. Okay, our horizontal asymptote would be y is equal to 1. And note that here, if you compute the limit as x approaches to minus infinity, again, you will get the same value. Okay. Why is that? Limit as x approaches to minus infinity, 1 over 1 minus 1 over x is equal to 1 over 1 minus 1 over, you put minus infinity here, right? Of course, you can kind of cancel these two minus signs. Again, you have the 1 over infinity form here. That is 0. So that means your answer is 1 divided by 1, which is 1. Again, your answer is going to be 1. Okay. So your horizontal asymptote in this case is y is equal to 1. This is the horizontal asymptote. Okay, let's work on the next part. All right, to find horizontal asymptotes, again, I need to find the limit. limit as x approaches to infinity, x squared minus 1 divided by x cubed minus 4x. Okay, so again, I divide both top and bottom by the highest degree term in the expression. The highest degree term is x to the power 3, right? So I'm going to divide both top and bottom by x to the power 3. Divide means multiply both top and bottom by 1 over x to the power 3. Okay, so we get limit x approaches to infinity, x squared minus 1 times 1 over x to the power 3 divided by x cubed minus 4x times 1 over x to the power 3. Okay, let's do this simplification. Limit as x approaches to infinity. If you do this multiplication, you get 1 over x minus 1 over x cubed divided by 1 minus 4 over x squared. Okay, of course, if you multiply this by this, that would become 1. And if you multiply this by this, you get 4 over x squared. Okay, now let's try to get the form. Okay, so as x goes to infinity, this takes the form 1 over infinity, right? At the top, I have the form 1 over infinity minus the second term. As x approaches to infinity, this also takes the form 1 over infinity. It doesn't matter whether you have cube o, square o, whatever the power, this becomes infinity again. Okay, so you have 1 over infinity form divided by 1 minus 4 over infinity. But I know that this form gives me 0. This is 0. This is 0. So my answer is 0 minus 0 divided by 1 minus 0, which is 0. Answer is 0. Okay. And even if you compute the left limit, I mean the left as x approaches to minus infinity, x squared minus 1 divided by x cubed minus 4x, using the same technique, you can see that that is also 0. So the horizontal asymptote in this case is y is equal to 0. And by the way, this is very clear from the horizontal asymptote theorem. Notice that, because in this example, we are asked to find use the limit concepts to find horizontal asymptotes. That's why we use this analysis. If you want, you can use the horizontal asymptote theorem to get the horizontal asymptote in a matter of seconds. Okay, as you can see, the degree of the top polynomial is smaller than the degree of the bottom polynomial. So the horizontal asymptote is y is equal to 0. Okay. But we need to obtain that using limits. All right, let's work on the last. Okay, how do you find the horizontal asymptotes of this one? Basically, again, you need to find what happens to the limit as x approaches to plus infinity sine x over x, and also what happens to this function as x approaches to minus it. Okay, this is clear because we know that this function sine x is always between minus 1 and 1, right? Doesn't matter how large x is, this value is always between minus 1 and 1. But as x approaches to infinity, your bottom goes to infinity. The top part is a bounded part. Top is bounded divided by x. Limit as x approaches to infinity. Okay. So your denominator is getting bigger and bigger. It goes to infinity, but your numerator is bounded. So your answer should be 0. Even when the limit as x approaches to negative infinity, the answer of this limit would be 0 because your top is bounded and your bottom is growing without bound. It goes to infinity. Okay, so the limit would be 0. So the horizontal asymptote would be asymptote is y is equal to 0. Okay, all right. Bounded. Okay, bounded, something bounded. You have in the numerator, you have something bounded. All right, let's move on. And then use limits to describe any vertical asymptotes of the following functions. Okay. So let's work on the first part. How do you find, let's first find the vertical asymptotes and then let's describe vertical asymptotes. How do you find the vertical asymptotes of this one? Well, you set your denominator to 0, right? If you set x minus 1 to 0, you get x is equal to 1. And clearly it is a vertical asymptote because x is equal to 1 does not make your numerator 0. That means it is going to be a vertical asymptote. Now, how do you, or in other words, at x is equal to 1, this will be a vertical asymptote. So your behavior of the graph would be either like this or like this. I don't know. We need to figure that out. Okay. We need to determine that behavior. How do you determine that behavior? Well, to determine that behavior, what you do is you compute the left and right limit. Limit as x approaches to 1 from the left hand side, f of x. F of x is x over x minus 1. What happens to this? As x approaches to 1 from the left hand side, this takes the form. What form would this take? As x approaches to 1 from the left hand side, this becomes 1, right? It's a positive number. 1 divided by, if x is approaching to 1 from the left hand side, this quantity will be approaching to 0 from the left hand side, right? Because x approaches to 1 from the left hand side means you put x values which are closer to 1 but less than 1. Okay, that means this quantity is negative. So this quantity will be approaching to 0 from the left hand side as x approaches to 0 from the left hand side. So you will get 1 over 0 minus form. That means answer is minus infinity. Similar argument will show that as x approaches to 1 from the positive side or right hand side, x over x minus 1 will take the form 1 over 0 plus, which is plus infinity. Why does it take this form? As x approaches to 0 from the as x approaches to 1 from the positive side, from the right hand side, this x takes the values which are bigger than 1, right? If they are bigger than 1, this quantity is positive, but it approaches to 0 because as x approaches to 1 from the positive side, from the right hand side. Okay, so this approaches to 0 from the right hand side. So you have 1 over 0 plus form, that is infinity. Okay, so that means your graph would look like this. Okay. All right. Let's look at our next example. I'm going to copy that to the others. All right, here is the example. If you factorize the top and bottom completely, you get x plus 1, x minus 1, x plus 1 divided by x times x minus 2, x plus 2. That's the complete factorization of top and bottom. Okay. All right. Again, to find vertical asymptotes, you set your denominator to 0. If you set your denominator to 0, you will get is equal to 0. That means x is equal to 0, x is equal to 2, x is equal to minus 2. Okay, that's what you get. So are all these going to be vertical asymptotes? Yes, because none of these numbers would make your numerator to 0. If that is the case, all these are going to be vertical asymptotes. Okay, our vertical asymptotes are these. Vertical asymptotes. Okay. At each of these x values, you are going to have vertical asymptote. Now we need to discuss the behavior of each vertical asymptote. What is the behavior of this vertical asymptote? Behavior means at x is equal to 0, how would your function be behaving? How would your function be behaving? Would that be going to positive infinity from the right hand side, or would that be going to negative infinity like this. You need to figure that out, okay? Or in other words, you need to find the left limit and the right limit. That's all it means, okay? So let's work with this first vertical asymptote, which is x is equal to, technically the first vertical asymptote would be this one, x is equal to -2, but let's work with 0 first, okay? Let's discuss the behavior. I want to find limit as x approaches to 0 from the positive side or from the right-hand side, my function g of x. Here is what you do. To get, I know that since this is a vertical asymptote, I know that this limit is either plus infinity or minus infinity. I need to figure out what infinity that is, plus infinity or minus infinity, okay? So let's figure it out. What you do is you kind of make a sign chart, okay? So you construct a sign chart for this expression. This is my g of x, right? Let's see what happens to each of these expression as x approaches to 0 from the positive side. Okay, if you look at this one, look at the top expression as x approaches to 0 from the positive side. This looks like top you have a minus sign, -1, right? This is approaching to -1, or it is approaching to a minus number. So I put a negative sign. And then if you look at the second factor, as x approaches to 0 from the positive side, this is approaching to a positive number, which is 1. So I put a positive sign here, divided by, as x approaches to 0 from the positive side, this takes the form 0 plus. So I put 0 plus here. And then the next factor would be negative, because as x approaches to 0 from the positive side, this is approaching to a negative number, which is -2. Okay, that's negative. And what is the other factor? As x approaches to 0 from the positive side, that's a positive number. Okay, now you compute the sign. You have negative times positive in the top, that is negative. Here you have negative times negative in the bottom, negative times positive in the bottom, that is again negative. So you have this form, negative divided by 0 plus negative. But these two negative signs will be cancelled. You get 1 over 0 plus, which is plus infinity. But here, if you simplify the sign, you get minus times positive, negative, negative times positive, negative. So that negative and negative will be cancelled. You get the form 1 over 0 minus, so that is minus infinity. Okay. Likewise, I'm going to leave this as an exercise to describe the behavior at x is equal to 2 and x is equal to -2. This is exercise, okay? All right, that is left as an exercise. Okay, and also I want to leave this also as an exercise. This is relatively straightforward because the limit as x approaches the x is equal to 0 is the only candidate for a vertical asymptote. But if you look at this one, you can find the limit as x approaches to 0 sine x over x. Okay, so you are not going to have a that is 1. We know that from the previous theorem. So you are not going to have a vertical asymptote in this case. All right, so let's move on. I want to work on this particular example. Determine whether each of the limits that follows is initially indeterminate form or non-indeterminate form. Then calculate each limit. Okay, here is the first one. What do you think? Would this be indeterminate or non-indeterminate? This is clearly a indeterminate form, because if you plug in infinity here and infinity here, This looks like 3 to the power infinity, which is infinity. This looks like 2 to the power infinity, which is again infinity. You get infinity minus infinity, right? This is indeterminate. We know that from theorem that we discussed earlier. Okay. So we need to find some sort of a strategy to find the limit of this. Okay. So the strategy again here is that, let's work on part A. Here again, our strategy is x goes to infinity. I'm going to multiply both top and bottom by the largest term. Okay. If you look at these terms with powers, the largest term is 4 to the power x, right? So I'm going to multiply both top and bottom by 1 over 4 to the power x divided by, first of all, I multiply my top by 1 over 4 to the power x. And then I multiply my bottom also by 1 over 4 to the power x. And then let's simplify this a little bit. Then you get, as x approaches to infinity, if you distribute this 1 over 4 to the power x inside the parentheses, you get 3 over 4 to the power x minus 2 over 4 to the power x divided by 1 over 4 whole thing to the power x. Of course, 1 over 4 to the power x means 1 over 4 whole thing to the power x. I can write this, okay? If I distribute this with 1. And then plus, of course, 1. Why is it 1? 1 over 4 to the power x times 4 to the power x, which is 1, okay? So that's what I have. Now I can take the limit. In taking the limit, I want you to know a specific rule, okay? This rule will not be proving this rule, but you need to know this, okay? As x approaches to infinity, r to the power x is equal to 0, provided r is bigger than 0, less than 1. If this r is between 0 and 1, if r is a number between 0 and 1, then the limit of r to the power x as x approaches to infinity is 0. Okay. I'm not going to prove this result now, but you can always experiment these things. Take a particular number for r, which is between 0 and 1, and put a very big power here and see whether it is getting closer and closer to 0 when you make your x bigger and bigger. Okay. So those are things, interesting exercises that you can do. All right. Now, using that idea, we can find this limit. Notice that here, this looks like your r is less than 1. Okay. This r is between 0 and 1. This r is also between 0 and 1. You consider this as r. This is also between 0 and 1. Okay. That means the limit of this one. First of all, I can apply this limit to top and bottom separately. Limit as x approaches to infinity, 3 over 4 to the power x minus limit x approaches to infinity, 2 over 4 to the power x divided by limit x approaches to infinity, 1 over 4 to the power x plus limit x approaches to infinity 1. Notice that this is 0 from this result. Okay, this limit is 0. This is 0. This is 0. This is 0. So you have 0 plus 0 divided by 0 plus 1, which is 0. So the answer is 0. Okay. All right. Let's look at the next example. We are asked to find part B. Okay. Limit as x approaches to infinity, x to the power 2 over 3 minus x to the power 3 over 4. Okay. What's the problem with this, with calculating this limit? The problem with this limit is that if you plug in infinity straight away, infinity here and infinity here, then you get infinity minus infinity, right? Which is an indeterminate form. That's the trouble we are having. Okay, so we need to find some way to calculate this limit, some strategy to calculate this limit. Here is the strategy in this case. X approaches to infinity. I'm going to pull out the smallest of these two powers. Okay, I'm going to pull out the smallest of these two powers. I'm going to pull out x to the power 2 over 3. Okay, then you get 1 minus x to the power 1 over 12. This is what you get. Now let's see if we can find the limit from here. Okay, as x approaches to infinity, this becomes infinity. So it looks like infinity. And then what happens to this one as x approaches to infinity? See, you have a minus sign here. As x approaches to infinity, this whole term will approach to infinity. But since we have a minus sign here, it becomes minus infinity. So this minus sign works out. It looks like infinity times infinity, which is again infinity. So you get minus infinity as your answer. Okay. All right. Then the last part C, how to find this limit. Well, we need to do again some sort of, we need to use some sort of techniques to get the limit. What I'm going to do is, I'm going to use the substitution or change of variable. H is equal to 3 over x. I'm going to write this entire thing, entire limit statement in terms of h now. Notice that as x approaches to infinity, this takes the form as x approaches to infinity. H approaches to 0, right? Is it clear? As x approaches to infinity, this takes the form 3 over infinity. 3 over infinity, but this is 0. Okay, of course, 1 over infinity is 0, but then this is also 0. Okay, so that means as x approaches to infinity, your h approaches to 0. So I can rewrite this limit statement as h approaches to 0, limit as h approaches to 0, 1 plus my 3 over x is h. That's the change of variable I'm using. Okay, you will see why I'm using that particular change of variable. Something interesting happening here. Okay, 2 times my x is, if you isolate x from this one, you get x is equal to 3 over h, right? So let me replace this x by 3 over h. 2 times 3 over h, which will be equal to limit as h goes to 0, 1 plus h to the power 6 over h. I'm going to do one more modification, limit as h approaches to 0, 1 plus h to the power 1 over h, whole thing to the power 6. Okay, now I can send this limit inside. Then you get limit as h approaches to 0, 1 plus h to the power 1 over h, whole thing to the power 6. Okay, but last time we discussed the theorem which shows that the limit of this expression as h approaches to 0 is e. Okay, this is the definition of e actually. Okay, so you can put e here, you get answer e to the power 6. That's your limit. Okay. All right, let's move on to our next example. Use limits to show that the polynomial f of x is equal to x cubed minus x to the power 4 minus x cubed minus 11x squared plus 9x plus 18 behaves like the leading term x to the power 4 as x approaches to infinity and as x approaches to minus infinity. Okay, and then we are asked to use the graph to compare this result. Okay, So what does that ask us to do really? Well, I'll take my function, the leading term, to be g of x is equal to x to the power 4. What this asks you to do is that you are asked to show that as x goes to infinity, this function f of x and this function g of x, they behave like the same. Okay, their behavior is same as x approaches to plus infinity or as x approaches to minus infinity. I will show that as x approaches to plus infinity, the behaviors of these two functions, f of x and g of x, are same. Okay, I will leave the negative infinity case as an exercise. As x approaches to plus infinity, all what we need to do is we need to show that as x approaches to infinity, whatever the behavior you get from this function is the same as the behavior that you get for the function f of x. For that, let's compute the limit. Limit as x approaches to infinity. First let's compute the limit for g of x. This is limit as x approaches to infinity, x to the power 4, which is clearly infinity. Because if you put infinity here, you get like infinity to the power 4, which is clearly infinity. Okay. And now let's calculate the other limit. Limit as x approaches to infinity, f of x. What would that limit be? Well, limit as x approaches to infinity. Notice that my f of x is this function. Let me write it actually there. X to the power 4 minus x cubed minus 11x squared plus 9x plus 18. Okay. Notice that you cannot plug in infinity in this function to find the limit. Why? If you plug in infinity here, you get infinity to the power 4, which is infinity. Here you get infinity to the power 3, which is infinity. You get infinity minus infinity, right? That's problematic because infinity minus infinity is indeterminate. Okay, so we need to figure out some other way to calculate the limit. Of course, we can calculate the limit. Limit as x approaches to infinity. What I'm going to do is I'm going to pull out x to the power 4. Then you get 1 minus 1 over x minus 11 over x squared plus 9 over x cubed plus 18 over x to the power 4. That's what you get. Now I'm ready to plug in my limit. Okay, if I plug in infinity here, this will become infinity. If you plug in infinity, here you get infinity to the power 4, which is infinity. And then here, 1 minus, you get 1 over infinity form, minus 11 over infinity, minus 9 over plus, pardon me, infinity, plus 18 over infinity. Notice that all of these are 0. Okay, so you have 1 here, 1 times infinity, which becomes infinity. So as you can see, as x approaches to plus infinity, the behavior of g of x function, which is infinity, is same as x approaches to infinity, the behavior of f of x, which is also infinity. Okay, and I will leave the other case as an exercise. Okay, show the same thing for the case when as x approaches to minus infinity. It is very simple. Okay, all right. And finally, we are asked to compare these results using graphs. Here is the graph. As you can see, for larger x values, this is the graph of x to the power 4. And this is the graph of the other one, f of x. As you can see, they are almost together for large x values, either larger negative x values or larger positive x values. These curves are very close. But if you take very, very large x values, you will see that your curves are almost on top of the other. Okay. This graph shows you the end behavior or the behavior at infinity for larger values. Okay. Behavior when x is large. All right. with that, we conclude this section. And of course, with that, we conclude the first chapter as well. All right, I'll stop there and I will see you next time.